Hello everyone. In this video, we will learn how to find area under a parametric curve. Let us start recalling that when a function is if y equal to f of x is continuous and positive on values of x between a and b. In other words, our graph for this function is something like this. Positive, continuous, go from A to B. Then you have this region under the graph of this function. That guy is going to be given by the integral from A to B of f of x dx. So just simple integral will do the job for us. Now, the question is that what if the curve is a parametric one, parametric curve. In other words, the x and y are given by as functions of t. Well, let's say that x at some point for alpha, for t like alpha, it will give us a, and x at beta will give us b. Then, well, the integral which was there, so this is basically when you do eliminate t. You have a parametric one, you eliminate t, then you will get back to the original formula. Now, I start from that formula, and I want to bring in t here. So basically, I start the substitution x equal to xt. As a result of that, dx is going to be x prime t dt. So that is the first thing. Instead of dx, I'm going to write x prime t dt. For f at x0, f at x evaluated at t, this is basically y at t. So I will put that one there. And I know that for value alpha for t, I get a, so I put alpha down there. And for value beta for t, I'll get b for x, so I'll put that one there. And this is the formula which will work for us in general for all parametric curves. There's only two things that you have to note here. First thing is that remark one, unlike the graph of function, when you have parametric curves, they may self-intersect. So our curve must be non-self-intersecting curve. Well, when you work with function, you don't need to be worried about that because it's graph of function. But when you work with parametric quotient, the parametric curve could be something like this, and we don't want to deal with these cases. Well, you can find areas, well, the region, if you fix, you can do some works there, but for now, you don't consider those ones, okay? And the second thing is that here, remark two is that you see we should arrange the limits of t integral so that when you evaluate the lower limit of t integral at x, you get smaller value. And for the other one, you get the bigger value. In other words, the bounds for t integral, so alpha and beta, must be so that the lower one, when you evaluate the lower one at x, you get a smaller value than when you evaluate x at the higher one. While a and b themselves, beta can be bigger than alpha, but the only thing matters for us is that we have to check that x at alpha is less than x at beta. In other words, x at lower limit of our t integral must be less than equal to y at upper limit. So if you consider all those ones, then you have basically the theorem. Consider non-self intersecting parametric curve defined by set of equations like x equals to at xt, y given by y at t, and x at alpha is less than x at beta. Then and also we have to make sure that y is positive and y t is positive on the given values of t. Then the area under the graph of that parametric curve is given by integral from alpha to beta y at t times the derivative of x at t dt. Well, I am assuming that you see that when I differentiate, it must have continuous derivative. X must have continuous derivative. So this is the fact that we will use in our examples and in this section. Okay. Let's do some examples. Find the area of an ellipse of x radius a and y radius b. Okay, so I need a parametrizations for ellipse. Since all the ellipses with the same x radius and y radius have the same area, I can go ahead and consider the ellipse which is centered at origin. So I will take a cosine t and b and y to be b sine t. And just a second, we see what is happening here. If we go like that in that direction, this is a, this is b. And if you start from 0 to 2 pi, this will finish whole thing. So from 0 to 2 pi, this will give you everything. But note that for values t between 0 and pi, y assumes positive values. So we have to consider only that part, and that is and that gives us half of the area of the whole ellipse. Okay, so that's the first thing to note. The second thing is that so you have to determine what is the lower limit in t integral and what is upper limit in t integral. You may go say that, okay, I'm going to put alpha equal to 0 and beta equal to pi. But see, if I evaluate x at 0, it's going to be a cosine 0, which is a, and x evaluate at pi, it's going to be a cosine pi, which is negative a. Okay. okay? And you see that x at pi gets smaller value than x at 0. So that means that our area here, half of the area of ellipse, is going to be given by integral. Remember, y t x prime t dt. What is the lower limit? The lower limit is the value of t which gives you a smaller x. Here is pi to 0. If you don't do that, you will get a negative number. Area cannot be negative number. So then I can plug in the values. Pi to 0 be sine t, and x prime is going to be a negative sine t dt. And that gives us minus ab. These are constants. From pi to 0 sine squared t dt. I have a trigonometric integral, so minus a to b. What I do here is use the half angle formula, half of 1 minus cosine 2t dt, and then I can go ahead minus ab. Well, find antiderivatives. Half of t minus 1 over 4 sine of 2t. And this is going from pi to 0. Here, minus ab. I'll just do the inner ones. A half of 0 minus 1 over 4 sine of 2 times 0 minus half of pi minus 1 over 4 sine of 2 pi. Yeah. I need a smaller one and then bigger one. But you see, this guy is 0, this guy is 0, this guy is 0. The only remaining term is this piece here, which is negative half of pi. There's another negative pi. This is going to be AB divided by 2 times pi. And then you see that the area of the ellipse here then it's going to be twice as that. Remember that this was half, so now twice as that, which will be pi times a. Okay, so that is the area of an ellipse with x radius a and y radius b. By the way, when a is equal to b, then the ellipse will turn to a circle, of a radius a. So then the area reduces to pi times a and b are the same thing. Yes, so I can write pi radius squared, which is what we expect to have when it comes to a circle, area of a circle. Okay, so this was the example. So remember, the formula you should keep in mind is this. The only key point that you have to make sure that you know is that this is true when y is positive and the limits are chosen so that the x evaluated at lower limit is less than x evaluated at upper limit. Okay.